Okay, it's time to introduce you to the t-distribution. We've been focusing so far on the normal distribution and large sample sizes because it's a perfectly good model to explain to you hypothesis testing, sampling distributions, power, all of this stuff. And now it's time to start extending that to other types of studies. So in order to use the normal sampling distribution like we've been doing, we have to either have a very large sample size or a normal population where the standard deviation is known. And any time where we have a smaller sample size and we don't in fact know the standard deviation, we estimate it from a sample, we're going to use the t-distribution. And as a historical note of interest, it was someone, William Gossett, who worked for Guinness, who developed the t-test. And it's called the student's t-test because that was a pen name that he used to publish it. He wasn't allowed to publish as an employee of Guinness because it's a corporation, and so he made up a name and published it anyways. And it was important for beer, I imagine, because they would first make small batches to test out some process and want to know. So suppose we measure the alcohol content of these 5 small batches of beer, we want to know if it's changed from the usual that Guinness is supposed to be. So, there's some variability from one batch to the next, but we don't know if it is a cause for concern without repeating it a couple times, measuring the variability, and saying whether it's actually different. And that was the real life application that led to development of the t-test that we now use for everything else you can imagine almost. And by the way, the thing that it came out of was that he noticed that with these small batches, so a small number of observations, the variability was actually greater than you expected from your standard error calculation. So he was rejecting his null hypothesis more frequently than he should have, even given if there was no difference in the brewing process. The way that we go about using the t-distribution, it's very similar. You calculate a t-statistic in exactly the same way as you're accustomed to calculating the z-statistic, and the only difference is this, that you use a standard deviation that you estimate from your sample rather than a known standard deviation from the population. It's very practical because most of the time you don't actually know a true standard deviation, you can only estimate it. And then the standard error, you can calculate in the same way, and you get your t-statistic in just the same way. So this is divided here by a standard error. The only difference is that when you calculate the t-statistic, you're going to use a different distribution to look it up in, a different table. You're going to use a table of the t-distribution instead of the normal distribution like you've been doing. And one difference with the t-distribution is instead of there just being one, you'll remember you looked up values of z, there was a table, you used rows for the first decimal place and columns for the second decimal place, but it was just one standard normal distribution. There is a different t-distribution for every sample size. And for every sample size, you're going to calculate what's called a degrees of freedom. And for a one sample test like this, it's very simple. All it is the sample size minus 1. And then you're going to use that to look up the correct t-distribution. Degrees of freedom is something, there are different ways to think about it, but it's sort of the amount of extra observations you have to calculate a certain statistic. So for calculating a mean, you only absolutely need one observation to do that. So if you have 2 observations, you have 1 extra, you have 1 degree of freedom. So it's kind of the amount of extra data you have. Another way to think about it is if you were given this test statistic, how many data points could you take away and figure them out again to get that test statistic? So if you have a sample size of 10 and you know the mean, you could take away one of those samples and then just try different values and figure out what that one observation was, because anything else will give you a different mean. It's not always intuitive, though, the degrees of freedom. The important thing is just that you know how to calculate it for a given test. And it's useful to know how to calculate because it will tell you if your statistical software is giving you a wrong answer because you're accidentally using it incorrectly. If you know how to calculate the degrees of freedom for a t-test, and then you see that in your SPSS output it says something different, it might be because you've made a mistake. And there are cases where that happens. Most common case is where you are trying to use a categorical variable, but it's been coded as a continuous variable, and you do a regression, you'll have the wrong number of degrees of freedom. And the only way, or the most direct way to figure that out is by doing a little calculation yourself of what the degrees of freedom should be and comparing that to your SPSS output. So, and sometime later I'll provide a summary of how to get degrees of freedom for several different tests. But for the one sample t-test, it's just n-1. So there is a different t-distribution for each sample size, but all of them are symmetric about 0 and all of them are bell-shaped. So they look kind of like a normal distribution, but the thing is that they're wider than the normal distribution. And the fewer degrees of freedom, the wider it is. The more degrees of freedom, the more narrow it is, and the more similar it is to a normal distribution. So in fact, if you get up to a really big sample size, n equals 1,000 or something like that, it'll look basically identical to the normal distribution. And as you get down to n equals 4 or something, it looks quite a bit wider than the normal distribution. So, and you can think about this kind of intuitively in that, remember when we knew what the standard error was, we could calculate, we knew what the variability of sample means would be. Now, when we don't know exactly what the standard error is, because we're estimating, we don't know the true standard deviation, we have to estimate it from the sample, there's actually more variability that you can get in your calculations of t, that difference in means divided by the estimated standard error, because you have some error in the standard error as well as variability in the mean. So you remember, in this, the x bar minus the mean under the null hypothesis divided by the standard error. Before, when standard deviation was known, we only had sampling variability in this mean. Now we have sampling variability both in this mean and in this standard deviation. So the values of t can vary even more. That's why it's a wider distribution. And why the fewer samples that you're using to calculate S, the wider the distribution is. This is just an example of what this table looks like. And here we have, for every row, a different number of degrees of freedom. And so as a result, you can't look things up as exactly, and the tables tend to only give you the critical values of t for common alphas. So you can look up what the critical value is for an alpha of 0.05 and any number of degrees of freedom, or an alpha of 0.01, for example. So it doesn't allow you to actually calculate a p-value from your sample. It just allows you to decide whether or not to reject the null hypothesis based on whether t exceeds your critical value. So degrees of freedom, it's your sample size minus the number of things that you estimate. So if you're estimating the mean, you lose 1 degree of freedom. Yeah. Yeah, it will start changing, especially when you do analysis of variance, where you're estimating the means of multiple groups. Each one of those, you lose a degree of freedom. There's that alternative explanation that I mentioned, that if you know the value of your statistic, like the t statistic in this case, how many observations can you take away and then replace them again? We use the t for normally distributed populations. That's an assumption that we have to make in order to use the t distribution. So whereas with a very large sample size, you'll remember it didn't matter what the population was distributed like because of the central limit theorem. Central limit theorem doesn't apply anymore because it's a small sample. So we have to make an assumption about the population distribution, that it's normal. But you can use the t statistic to calculate a confidence interval just like you did before using the table of z values. The only difference will be that value of t. And so for a 95% confidence interval, it's not just going to be 1.96. It's going to depend on your sample size. For a small sample size, this will be something bigger than 1.96 for a 95% confidence interval. And for hypothesis testing, rather than just calculating the p-value, if you're using SPSS, you just get the p-value. If you're doing it by hand, then you're going to calculate critical values of t and reject if the t from your sample is bigger than that. So there's the example with the brews. You have 5 beers, you measure the alcohol content of each of them, and you want to build a confidence interval for what the true mean alcohol content is going to be if you make 1 million of them, and is there evidence against some null hypothesis. And there's enough data here for you to go ahead and do both that confidence interval and the hypothesis test. So just to remember your assumptions, that we have a statistically random sample. That's always an assumption of hypothesis tests we do. And additionally, for the t-test, that it is approximately normally distributed. We we don't use it for testing proportions. We only make the normal approximation for proportions, and we only use them for large samples. So they are, however, robust to violations of the assumption of normality. And by robust, I mean that it will not cause you to make more type 1 errors. If your assumptions are violated, your power can go down, but you won't make more type 1 errors. So if you set alpha equals 0.05 and you have a non-normally distributed population, you're still not going to be more than 5% probable to reject the null hypothesis. Sorry, that's the property of conservativeness. Property of robustness is that some departure from normality is not going to have much effect on your test. It has to be a fairly strong departure from normality. And then on the next slide, I give some rules of thumb for that. With the exception that when you're doing one-sided test, it doesn't work as well as with two-sided tests. Another reason that we don't usually use one-sided tests. So here's some practical guidelines. If you have a small sample, less than 15, your data, your observation should be pretty close to normal. Once you get over 15, there can be some skew, and once you're over 30 or 40, you can have fairly strong skew and big outliers. And you use the tools that you've learned earlier in this course to assess these assumptions in any data set that you have. All right, so some quick Q&A, and then I need to let you get to lab soon. So is the t-distribution, does that describe a population or does that describe a sampling distribution? Very good. Describes a sampling distribution. So when we're estimating the standard deviation from the sample, instead of knowing it from the population, do we use the t-distribution? Yep, that's true. I'll go ahead and so is the 95% confidence interval larger or smaller when you use T compared to when using Z? What's that? Larger. Yep, it's larger, or it could be approximately equal if we have a large sample size. It'll never be smaller though. And as I already gave you the answer, but tell me anyways, as n increases, the t-based confidence interval becomes more similar to the z-based confidence interval. True. Yep. All right. So we've taught you all about significance tests. Let's talk about some limitations of them. One thing to remember about the p-value is it tells you about statistical significance. It doesn't tell you about practical significance. So when you have a small sample size, then even big differences between your study population and your null hypothesis, you're not going to see. So that you're going to get statistically insignificant results, even if there is a practical difference. On the other hand, when you have a very large sample size, and you're going to find this with the New York City Community Health Survey because it's a pretty big sample, even small deviations from the null hypothesis can give you a statistically significant result. So just because you have a tiny p-value, you have a p-value of 0.000001, it doesn't necessarily mean that that difference is important in real life. It just means that it didn't happen by chance. And confidence intervals can be more informative to that because because it actually tells you the size of the difference, whereas a p-value, that's just a probability. It doesn't have to do with the size of the difference. Oh, this is an example. So a paper about this called Too Big to Fail, Large Samples in the P-Value Problem, showing that for sales of cameras on eBay, these various, there were various things. One of them here is, what is this one? Some factor that you can change about what you advertise in a camera. It has a coefficient of 0.1, a p-value of 0, and the interpretation is here, oh, it's the minimum bid price. So if you increase your minimum bid by 1%, you'll get on average a 0.09% increase in final price. So we have a p-value of basically 0 here, but it's up to you to decide whether that is a difference that you care about when setting your minimum bid. That if you increase your minimum bid by 10%, you can get a 1% increase in your final price. Maybe it matters, maybe it doesn't. This is a big one, a common one. The p-value is not a probability that H0 is true. Very common misconception. Does anyone want to tell me why that's false? Okay, there's the answer there, but tell me in your own words. How about this example? Researchers did not find evidence of any effect of the treatment on self-reported pain because they got a p-value of 0.2. Does that mean there's an 80% chance that the pain reliever has no effect? Yep. Exactly. It just means that you don't have enough evidence to reject it. Obviously, if you don't try very hard, you collect a small sample, you're probably not going to reject it. That doesn't make it truer. It just means that you didn't have evidence to reject it. Another way to say that, the idiom associated with this is no evidence of a difference is not evidence of no difference. And yes, although 0.05 is the common cutoff, it's not a magic value. There's not actually that much difference between a p-value of 0.04 and a p-value of 0.06. And one case where this can come up is you often have studies that have more than one endpoint. So you remember that malaria intervention study? There was one endpoint that was anemia, one that was performance in math, one that was performance in spelling, and you can end up with, if they're correlated endpoints, a p-value a little over 0.05 and a p-value a little under 0.05. It doesn't mean that those are fundamentally different. It just means you didn't meet that threshold of evidence for one of them. So, but when you're thinking about it yourself, 0.06 is still some evidence against the null hypothesis. If you were going to bet even money, you'd probably want to bet against the null hypothesis. It's just you didn't have that 5% probability against type 1 error. So another way to misinterpret hypothesis tests is to forget that they're about the central tendency of the population. So they're about the average of the population. And I had some questions on the last exam about this, just to emphasize that it's about the means of the samples. It's not about the individuals. So we measure serum lead levels in a sample of 100 children from an area with potential lead contamination, find a mean of 5 micrograms per deciliter, which is less than a normal limit of 10, and reject the null hypothesis, 0.01. So does that mean that fewer than 1% of children have serum levels exceeding the limit? What do you think? Yes or no? No. Hopefully, think about that until it screams out at you as no, because that's a really bad misconception. It has nothing to do with individuals. It's just about samples of size 100. It's about the mean. It's about the mean serum blood level of children in this area with potential contamination. It's about their average. It's not about how many individuals are below that level. Hypothesis tests are about averages. They're about central tendencies. So if n is small, n is 6, does that mean you can't believe any results of a hypothesis test? Or conversely, if n is 1,000,000, does that mean that you have to believe the results? I don't think so, no. So why not? Well, the big issue is it a statistically random sample? If it is, then we have these procedures that you've learned, the t-test, they will account for the amount of variability that you get in a small sample like that. So if there's a big enough departure of that sample mean from your null hypothesis, then you should reject the null hypothesis. Now, if you have a sample size of 1,000,000, of course, you get a smaller standard error. It's easier to get a small p-value. But what if that sample size of 1,000,000 is a totally biased sample? It doesn't actually represent your target population. Then you could still have a wrong conclusion. So it is better to have a smaller representative sample than a bigger biased or unrepresentative sample. Of course, your hypothesis testing, your p-value, do not control for biases in study design. And in my field, in cancer genomics, there have been some very high-profile retracted papers and withdrawn clinical trials for reasons about this, because there were flaws in the study design where a sort of interview bias where they used a different set of experiments on the controls than they did on the cases, so they got small p-values, but it was just because of technical flaws of how they did the experiment. That has to be assessed independently of your p-value. Remember, of course, that your tests can be statistically significant by chance. That's what you control with the type 1 error rate. This is XKCD cartoon where they do the same study with 20 different colors of jelly beans, and then eventually find that the green ones are linked to acne after they've tried 19 other colors. So you'll learn later to control for that with multiple testing, but remember that with a p-value of 0.05, even if no jelly beans are linked with acne, by the time you test enough of them, you'll get a p-value under 0.05. What you read in the literature, about the difference of an effect size, very oftentimes the true difference between their target population and the null population will be less than what's reported. And that's because of a phenomenon known as publication bias, which is that it's harder to get studies published if you don't find a difference. So It's also called a file drawer problem, that the studies that don't find a difference, they get filed away. The ones that do find a difference, they get published. So even if it's no fault of the researchers who performed that study, that kind of bias can result in this sort of lifting of statistical significance and differences seen in the published literature. And it's really once you have some replication by independent researchers that you start to get an accurate idea of what the difference between this target population and the other population really is. And there are some high profile examples of this too, especially in drug trials. We're a little more careful now about drug trials, at least those that get approved by the FDA, but in other types of trials, there aren't those kinds of protections to protect from all of the different drugs or all of the different studies that didn't find statistical significance, just not getting published. Okay, I can let you go to lab now.